I am a firm believer that for most of you, unless you get into statistics or higher level math, and by higher level math, I mean graduate level, that most of in fact, all of your mathematics is just going to be us trying to awaken within you truths you already know, right? Like for example, if I talked about being able to factor, right? Factoring we've already described as making of rectangles. So I could say, can I factor 6? I could give you 6 marbles and ask you to organize those marbles so that they make a rectangle. Could we do it? Right? We would get a 3 by 2. Could you, if I gave you 7 marbles, could you organize that into a rectangle? Only one way, and that would be a 1 by 7, right? You just stack them all up in one single row. And so if I'm going to teach you about prime numbers versus factors, I'm just going to pull on that because that's what factoring is. It's the ability to organize it in a rectangle, right? Prime numbers are those that you cannot organize into a rectangle other than just simply lining them up. Otherwise, you can describe them in terms of other lines, other organizational patterns, like lines of 3, multiple lines of 3 would be 6 or 9 or 12. So again, it's not about like me trying to show you something new. There are other classes for that, right? Like anybody here going to be studying law, or what would be another one? History. Another one would be physiology and what's the word I'm thinking of? What's the study of the human body? Anatomy, right? Anybody here studying any of those courses? Not a single one, maybe, right? Chemistry gets kind of close, right? Biology, anybody here going to biology? We got a few there, right? So like the biology, like that field, those fields, you're just going to have to memorize things. Like you're just going to have to memorize things. And there are mnemonics, there are patterns for sure, right? Everything's not abstract. A lot of them have Latin roots, and you can figure out what the Latin roots are, and then you're better at being able to memorize everything together. But like, this is just not that class. This is just like, it's never that class. There's only one reason to take a math class at all, and that is to develop within you a logical and mathematical mindset. So if there's ever anything we're not doing that makes sense to you, you are literally wasting your time, right? And it's just not going to work. It's not a successful strategy. So again, how many engineers we got going in here? How many computer science? And then what else do we got? We've got medicine, right? Anybody going into bio, right? And then what else do we have? Chemistry, right? So in all of those, you all want to play active modeling roles in your field, right? There's no place to just document, right? Computers have taken that part over. So our job is to kind of learn how to model and describe. So we got to practice that now. We're going to kind of start today. Today is the one that I've been leading us up to. Today is going to be a little bit challenging because I'm going to be throwing some Greek letters at you. I'm going to be throwing some big ideas at you. However, again, the importance is for you to interrupt me if I lose you, because I've been slowly alluding to this for a while as a way of trying to build up your comfort with the language that we will use today. So, for example, limits. If we go back through our story of limits, I've shown you limits as data would suggest them to be. I've shown you limits as graphs would suggest them to be. I've shown you limits as stories would suggest them to be. But there is a small little bit that I'm actually going to credit Julia for continuously picking up on, because every time I say limits and I use it informally, I see like you're like looking at me like you don't believe me. And it's kind of because I haven't been able to really pin down some of the details for it, because the details are complicated and I have to leave that to the end, otherwise it just doesn't work. Like, for example, whenever I've said forever, forever is not specific. That's why we've moved away from it. Whenever I said we could plug it in, I usually had to have like a nice 5-minute narrative discussion with you all that never showed up on the paper. And so it was like, how are you all supposed to show your work if not through the paper? And how am I supposed to convince you if I'm not in the room to have a discussion? Like there's a little bit of a gap there that I've just kind of been leaving. And it's because In this course, you will not be required to fill in that gap formally each and every time. However, you will be required to think about it. Because if you think about it, it will tell you the times that you are good with using the strategies we've discussed in this class and the times that you are not okay to use the strategies that we've discussed in this class. And so we're going to kind of pin down the actual formal highest level of rigor that we could use for limits. And then we're pretty much not going to touch it again because it's very, very complicated. It gets to be very, very dense. And so I have to show you only very small, simple examples so that you understand the idea that is supporting everything. But I'm not going to make you actually prove it with every problem. Okay, so we're going to kind of get into that a little bit here. So let's talk a little bit about limits. Informally, I have slowly moved our language from where I talked about approaching it forever. That's okay language. That's okay language, bad proof. Because if I say forever at any point, then you have to show me the forever part in your math. And it's very difficult to show me at forever, because that means you're never done, and so we're never finished. Like, forever is a good word to discuss, bad word to prove. So instead, we talked about it as a sequence, a list of data. And then something that says at a certain point, I can cut that list of data, and all data after that point will be getting closer and closer and closer. And we say, great, but then how do I prove that without looking at each and every data point after that? And we said, well, we can kind of just look at trends and use our knowledge of graphs and our knowledge of growth and behavior, but we had difficulty showing that on the paper. So I'm going to show you what it would actually look like if we put it on the paper. It gets to be a little dense, but that doesn't mean that the story is any more complicated than what we've been talking about. At the end of the day, it is still the logic of approach. It is still the idea of being able to find a point where we cut something off, and afterwards we are close enough, and that close enough can be made as close enough as we ever want, and that's a good way of proving that it approaches forever, is because we could always just have this kind of cyclical cutting off and cutting off and cutting off that gets us better and better and better. So let's remember that we've got this definition here. A limit exists if a sequence of data can be cut off after a point, and all further data is within some tolerance. We're going to call that epsilon. So think about it in the same way as you would look at these asymptotes. Let's remember, how do we know there's an asymptote at -2? Visually, because it gets really close. How do we prove that it gets really close? Well, what I'm proposing we do is we not have conversations about the -2 because it never touches the -2. And we don't have conversations about there's a dotted line at -2 because I could put a dotted line anywhere. That what we do instead is we say there's a certain x value where I could cut it off, and then look at that gap. That gap is so small. And you'd say, yeah, but that's not close enough for me. And I'd say, but logically, I could find another x value I could cut off that's even later, and that would be even smaller. And so we can get some sort of discussion going about how if I can always find a place to cut off that meets any required tolerance you want, that the only way for that sentence to be true is that we are forever squeezing it. Right? So it's a way of trying to capture forever squeezing as, no, I just have the ability to forever match any required gap, any required tolerance. So the idea of using tolerance is a big, big indicator here for anybody who's going into engineering. Like, tolerance is a big engineering word. This is a good one to start getting comfortable with. Does anybody have any questions about this definition? Because I want this to be rock solid before we start to get into how I express it through my math. Yeah, go ahead.
Can you phrase tolerance in a different way?
Sure, tolerance is a gap, right? So it's just saying, like, if I needed to convince somebody, they might say, I will only believe that you are approaching an asymptote at -2 if your height is always within 1/1,000,000th. And I say, good, I could find an x value, which after that, my gap is always less than 1/1,000,000th. But we're going to, instead of locking down 1/1,000,000th, we're just going to call 1/1,000,000th epsilon. Because if I leave it general, then I'm able to have a discussion that says, I'll give you a recipe. Whatever tolerance you want me to hit, I will just give you a method by which you can find the place of cutoff. And that because I leave that general, and because it doesn't matter what you give me, I can always find a cutoff. That's another way of discussing forever approach, is that just I always have the ability to cut it off and meet any expectation. Does that help? Great. Anybody else? Okay. Let's do an example, just a real world example. This one requires that we remember that if I have the real number line and I throw a dart at it, it is 100% guaranteed that that dart will land on an irrational number. Right? Let's remember all the way back. Remember when I was showing you how big the quantity of irrational numbers are? And it was like there's a whole bunch of irrational numbers, right? In fact, the entire length of the number line is due only to the irrational numbers, because I can cover up all of the rational numbers with less and less cloth, less and less ribbon. That's an example from earlier back in the semester. So what this is going to do is we're going to pull on that, because the result of that logic is that all things that exist on a continuum, like for example, my height, am I 6'2"? It's impossible for me to be 6'2", because 6'2" is a rational number. I am guaranteed to be an irrational number because there's just so many of them. So whether we call it rational or whether we call it anything, it's irrational. It's always irrational. The world, if it's measured on a continuum, is irrational. What's the size of that desk? It's an irrational size, guaranteed. Guaranteed it's an irrational size. What's the length of the desk? It has to be an irrational number. There's just too many irrational numbers for it to land on a rational number. They take up no space. The chance of me choosing something that has absolutely no width to land on is impossible. So the irrational numbers make up the world if they're able to be measured on a continuum. So let's talk about, for example, an old-timey radio. This is a good model for it. I want you to imagine one of the ones that has like a knob. You can adjust it. So let's imagine that there is a radio station and it is broadcasting. I don't know which station it is broadcasting on. I don't know its frequency. However, I turn the knob so that it's pretty close to 97.1, and it sounds pretty good. However, can I ever tune the knob so that it lands exactly on 97.1? Let's first check. 97.1 is a rational or an irrational number? It's a rational number. What's the likelihood of me landing exactly on a number that takes up no space on the number line? 0. It's impossible for me to do that, right? So if I'm trying to get close to 97.1 at every point, I am landing on a rational or an irrational number? Irrational. I have to be landing on it. Yeah, go ahead.
Second example, but an irrational number, so it's 97.1. If it's irrational, what would you do?
Sure. Square root of 2 would be 1.7-ish, right? 1.7 and a bunch of decimals after that. So I might land on 97 plus square root of 2, which is an irrational number, but it's pretty close to 97.1, no irrational, right? Or, I mean, it could be any other number after that. It could be 97.135925, any other pattern that has no pattern, right? Any other decimals that have no pattern. So I'm landing on something close to 97.1, not exactly 97.1. So are we all comfortable with the fact that like anytime you have ever tuned one of these radios, at every moment of its existence ever, it has been landing on an irrational frequency? Because otherwise it's impossible for it to have picked out the perfect spot to land on a rational number. Again, just checking in here. How do we feel on that? Give me some feedback. I've got like 5 of you. Give me some thumbs up. We feel all right? If not, this is the time to ask. Okay. So we have to start that as a given. It's impossible for me to land on a rational number, but I can get kind of close. Now, if I land on this number and the signal sounds pretty good, I could make it sound a little better. Maybe I fine tune it a little bit. Maybe I bring it in so now it's 97.115238, blah, 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 blah. That is closer, and I hear a better signal. I could bring it in a little bit more. Maybe this time I accidentally overshoot it a little bit, but it's still pretty close. And that's even a better signal. And I can continue to fine tune this over and over and over and over again. Will I ever exactly hit 97.1? No, it's impossible for me to choose a rational number when the magnitude of irrationals outweighs it so severely. However, I could make an argument that because I continue to get closer and closer to 97.1, that the only logical conclusion would be that the radio station truly is 97.1. So they must be broadcasting on this frequency, not because I landed on it, but because as I got closer and closer to it, my signal got better and better. So in other words, what we're describing here is tolerance. Within a certain amount of gap around that frequency, I will get a radio station. If I start to bring that tolerance in, I will get better and better signals. If I continue to bring it in, I will get a better and better signal. And because I could forever bring it in, that must be the signal. How do we feel on that? If I need to talk that one out? Yeah. Very good. So that will be our way of proving limits. Now we're no longer going to be doing logic of approach. Now we're no longer going to be doing data. What we're going to build is a tolerance box, a logical tolerance box. And we're going to argue that that tolerance box can be shrunk in around the true value. And that if I can shrink it in around the true value, that will be my method of figuring out the true value, even though I never actually have to touch it. Again, anybody got any questions on that? Think of it like we're just honing in on a signal, right? I don't ever have to hit the signal. I just got to get closer and closer and closer and closer until I go, that must be the signal. Yeah, go ahead.
I'm kind of class.
Yes.
That starting temperature and we have final temperature that we're trying to how do we still hit that middle temperature?
Good. So on that one there, when we had some kind of continuous change, the only way we couldn't have hit that middle temperature is we would have needed to either have an interruption that skipped it, which didn't make sense with the idea of gradual change, or we would have needed to somehow violate our initial conditions of actually starting somewhere and ending. So like it becomes a natural conclusion of saying I have to go through and flow through everything in between. Now, the parallel I'm drawing is, have you ever measured water's temperature to be exactly 205 degrees? Never. The thermometer might tell you 205 degrees, but that's just because the thermometer cuts off at a certain point and gives you only so many decibels. But the true existence of that temperature would be on the continuum, and because it's on the continuum, it would never squarely fall on a rational number. Which again, so the different model, I wouldn't blend them too much, but that's the idea. It's just simply saying if I have a behavior, I can pin down when I hit something. But if I go out into the real world and I try to measure, measurement in the real world never will give you nice answers if it's allowed to exist on a continuum. Okay, let's start to bring this back into some math examples. So again, if I can be around 97.1 and forever refine my proximity to 97.1, and the radio signal keeps getting better and better as I get closer to 97.1, I don't ever have to touch 97.1, but I can still make a conclusion that the frequency is 97.1. It's a way of saying I can figure out what something is without touching it. And that's beautiful logic, because limits are never about touching. They are always about squeezing in. So let's do an example here. I've only got 2 examples, and in these examples, I've got to choose the easiest ones, because otherwise the language and the proof gets a little intimidating, overly intimidating, more than it's worth for this level of math. So if I ask, what is the limit as x approaches 3 of 2x minus 1, what will that be? Who can tell me why? Let me see a hand. Go ahead. So algebra doesn't tell me anything about approach.
Right. But if you're approaching 3 on the x-axis, you can put in 2.99.
Okay, good. So pause it for a moment. When you said approaching on the x-axis, tell me how you saw that, or tell me how you knew that.
Because close to 3 and 2.
Good. So that means that you're accepting that you were wrong at every step in the journey, but that your answer is true. Right? Like that, do you see the barrier of using data? Data doesn't give us the answer, because data is literally estimate, 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 which is good for insight. It's good for us. It's bad for proofs, because we don't want to say, I guessed, I guessed, I guessed, I guessed, I knew. That doesn't flow. But nonetheless, you all are correct. Like, I would accept that answer. I would accept that logic. I just want you to recognize it's not formal, that it does have inherent logical flaws. Somebody else, how did we see it? How did we, or what did we do? Did anybody like look at the graph? Yeah? So in that case, if you're like, oh, I saw it, I could imagine the approach, then all of a sudden we're having a discussion where I have to imagine that I trust your eyes and that I trust your imagination, neither of which is logic. Because you could be seeing something very different than I'm seeing, and we could never prove that to each other. Right? Plenty of people will like look at the shirt and they'll be like, oh, that's like dark brown. And other people will be like, no, it has gold in it, and gold flecks. We got to have a conversation about what we see in eyes. Like, that's just bad. We don't want to play that game. So instead, we're going to have a conversation about a tolerance box. I'm going to argue that if I look nearby 3, that any of those x values will fit in a box around A. I can define the box. I can get the length of the box, I can get the height of the box, and I can say if you make the box shorter, then the width has to squeeze in. Or if you squeeze the width in, the box will have to get shorter. And I can now make an argument without ever touching A, that as this box shrinks, A will be the only thing always contained. You see how that's that idea of tolerance? I'm kind of trying to narrow in. I'm trying to zoom this in and show that the limit can be estimated not with specific data points, but with an argument that says it's the only thing I squeeze towards. So again, we're going to stick away from ideas of plugging in. For this conversation, you have to have a really good reason to say, I can figure out a limit by plugging it in. Like, you got to have a good reason. We actually gave you that good reason. What's the good reason that allows you to plug it in? We brought it up last class. The only time you're allowed to say that the limit is the same thing as what I get when I plug it in. Continuity, there it is. If it's a continuous graph, then you're allowed to plug it in. So we could make an argument that lines have no interruptions, so we could get the same answer by plugging it in. That would be a fine argument, right? That would use continuity as a backdrop. I'm just showing you a different one that works even if the graph is not continuous. Okay? So here's how it goes. Here's the strategy. The strategy is going to be, if the limit as x approaches 3 is 5, then there should be a neighborhood around 3, a little bit to one side, a little bit to the other, such that we only get function values near 5 in that neighborhood. So in other words, if you say, I need you to be really close to 5 for me to believe you, I'll say, no problem, I can find that neighborhood. And in that neighborhood, I will have limited the only data you could possibly collect as being within your close enough. So that's the way we're doing it. We're not cutting off the graph like we would at an asymptote and looking on. We're cutting off a graph near the value and looking in. It's a way of being able to talk about limits when I don't actually ever have to touch the point. All right, so said another way. Again, I'm trying to give you lots of different backdrops before I start bringing in the math. Said another way, if you asked me to prove that I can squeeze my y values within epsilon, whatever tolerance you want to give me, I have to be able to provide you with a recipe that cuts off the graph in some neighborhood. So if you say I need to be really close to 97.1 to believe me, I'll be like, good, then your little needle on the radio has to be within this space. That's what we're talking about. Okay, let me show you how we do that. Okay. We're going to start with building a conversation. Let epsilon be a tolerance such that epsilon is greater than 0. So that just means I'm beginning the conversation assuming that you will challenge me and require a certain amount of precision to believe my limit. Somebody remind me again, what does epsilon mean in terms of context? It's what? It's the, I just need to be a little louder. The width, well, so like the height you're talking about? So we've got a height, it's a gap. It's a gap, good, between my proposed limit and any other height nearby. So what we will do is we'll set it up just like that. Then the difference between my function and 5 has to be less than that gap or bigger than the negative of that gap if I'm a little under. Right? So that just means like if I say the limit is 5 and we find a data point, right? The data point is 4.99. That should be close enough, right? And if it's not close enough, we would just find a different data point. So that's all we're saying right now is that I can find data points that are you're close enough, you're within your epsilon. Again, I'm pausing here at every moment to give you a chance to raise your hand if I'm losing you. Do we feel pretty good that all of the heights in this picture are going to be within epsilon above and epsilon below? Good.
You set the epsilon, right?
It's me leaving an opportunity for somebody to fill that, right? So somebody can come along and say, I need to be convinced with this tolerance. And I'd say, good, we'll just plug it into epsilon. I'm going to leave it general and not as a number so that we can use it as an expression no matter what challenge people want to throw at us. Because again, we all know the answer is 5. We've just got to convince people who might not believe us. Okay, watch what we can do from here. Watch how all I'm going to do is reframe exactly what we have. Instead of f of x, I'm going to write f of x.
that I can massage this and simplify. But because remember, f of x means what? Wouldn't be width, be heights, right?
Yes.
It'd be function heights, heights on the graph. So I'm just saying that I have heights that are near 5, which makes sense for limits, right? So I've got heights near 5. Watch, we can do a little bit of, again, just some simplification. We could divide all things by 2. And now I pause, and I remember what this is talking about. I'm trying to find a neighborhood around 3 that matches your required tolerance. Well, this right here, this says around 3. This is x compared to 3. That's what that says. In the same way that this was heights compared to 5, this is x compared to 3. We could give that a name, like we could call that delta. And if we want to be really slick with our math, we could rewrite this in terms of absolute values. At this point, it's just symbols on the paper, but it's important that we recognize the story that symbols tell us. This says, if you want to be within 1/1,000,000th, so we make epsilon 1/1,000,000th. So I get a very small little box in here that I've got to be within, that I can make that happen. I can make that happen. I can get that close. I just have to be within 1/2,000,000th of 3. I just have to be super narrow around 3, and then that will restrict all of the heights to be super narrow around 5. And if you said, no, I want to make it tighter, then I'd say, good, plug in any number you want for epsilon, and I just need to be half of that gap around 3, and I will be restricted to giving you only the heights that will satisfy your requirement. And again, doesn't this kind of make sense that if I look at this little tolerance box here, that this tolerance box follows a slope of 2. So doesn't that make sense that the height of this tolerance box is always going to be connected to that width, where that width is half the height? After all, that's what slope says. Slope says I go up 2 and I go over 1. So it makes sense that for the width, if the width is width, that the height would be double that. Or if the height is given, that the width would be half of that. So it's just saying this is no problem. I can prove the limit is at 5, because however close you want to get to 5, I just have to get half of that distance away from 3, and I will only be giving you data that matches your requirement. In other words, if we want to bring it back to that radio analogy, if you say, I need you to be within this of 97.1 for me to believe that 97.1 is the true frequency, then I say, no problem. Then we just need to get that little vertical bar within this space. Let me pause here for a moment. How are we feeling? I've got a bunch of people thinking, a bunch of people staring. Go ahead, Mikhail.
So our delta is going to be which is
Epsilon. Epsilon. So epsilon's the gap. you think of it as a tolerance, right? So it's our saying, I will believe you if you are within this tolerance, within this epsilon. And I say, no problem, no matter what you ask of me, I can find that, of course, because the box will shrink around A forever. How do I show that it will shrink around A forever? I say, no matter what height you give me, I just need to be half of that width around 3. And so long as that statement stays true, as you shrink, I shrink, and we tunnel in towards A. Feeling all right? Again, this is a good chance to talk it out loud. It's a language. It's hard. It's a dense proof. You're thinking on it. You want to come back to it, or you want to phrase it out? Yes, exactly right. Just like with an asymptote, we were trying to cut off the asymptote so that we only looked at heights nearby, whatever. Here, we're trying to cut off, but we've got to exclude on both. Like, we got to exclude everything else. So that forces us to make kind of a box, and that box can be made forever more and more towards our limit. Good, good. Let's do another example. Let me show you that we can kind of take this and start to run this through a little bit faster. Let's again just remind ourselves that at the end of the day, we're building a tolerance box. Here's better. What's my favorite shape? Oh my golly, it's rectangles all over again. Like, all I'm doing is I'm just saying now I can build a rectangle around my limit, and that rectangle I can describe with variables so that that rectangle is allowed to shrink as far as I want it to shrink. So if we graph this, we already know that 5x minus 7 is going to be something like this. And if we say, what is the limit near x equals 4? Not only is the height actually 13, but we can expect that it's going to shrink in towards 13 as I get closer and closer. Now, real quick, if I imagine a tolerance box around this whole thing, how much taller will this box be compared to its width? What would be? Where's 2? How much taller will this be versus its width? Where are you getting 5? Doesn't it make sense that I go up 5 in ratio to how much I go over 1? So the height's going to be 5 times bigger than the width. So that means that already I can predict my answer from this. Like, I should be able to say, if I get within 1/5 of my required height, then I can match it. Right? So let's watch how we do this. We say, let epsilon some height be given greater than 0. Then I could say the difference between any of my function values and 13 should be less than that value and greater than its negative value. Because again, like, I might be under, right? I might be off by a negative amount, but that still should be within that size. And then we just work this through. We say, okay, then that means that everything I get after I plug it into the equation should be within that height. Oh. And we get exactly what we would have expected. My gap away from 4 has to be 1/5 of my gap away from 13, because I've made a tolerance box that is 5 times taller than it is wide. Go ahead.
Makes the absolute value is just taking away the negative.
The absolute value means distance, right? So it says the distance between x and -4. We already know that the distance between x and -4 has to be below this, and its negative difference has to be above this. So I'm just recombining all of that to say The size of that distance has to be below the size of my boundaries.
Then there's for immediate in that term, or for the absolute value of delta.
Technically, what you want to do at this point is you want to say this right here is what we called delta. So I just need to get my width, that's what delta is, the width of my tolerance box has to be less than 1/5 of the height of my tolerance box. So epsilon is just the height away from my limit. Delta is just my width away from what I'm trying to hone in on, what I'm trying to approach.